Lesson 7, Representing Text. The objectives of this lesson are to determine the number of bits per symbol needed for a representation system based on the total number of symbols it is necessary to represent. It's a lot of representing. We're going to use the decimal number system when designing ways to represent other information in binary. And we're going to explain how bits are grouped to represent abstractions like numbers and text. Now, previously in AP Computer Science Principles, it was discovered that representing more numbers, bigger numbers, meant requiring more bits or needing more bits for each number in order to avoid overflow. Values represented by bits may have rounding errors due to some values being more precise than we're able to represent by the number of available bits. So we learned about overflow and rounding. Now, by the end of today's lesson, you should be able to define the following vocabulary: abstraction, ASCII, and protocol. When we communicate on the internet, we usually send text, not numbers, back and forth. Today, we're going to look at how to use numbers to represent text. First, a warm-up. Look over here at the right, 1, 1, 2, 14, 7, 4, 10, 31. Think about what this list represents. When you think you know what this data represents, add another entry to the list and be ready to explain the meaning. Pause the video and jot down your answers in your notebook. Great. Did you realize that each item in the list represents a non-denominational holiday? New Year's Day, Valentine's Day, Independence Day, and Halloween. You could have picked Veterans Day, Juneteenth, Memorial Day, Labor Day, a bunch of other non-denominational holidays. Okay? But we had 1, 1, 7, 4, 2, 14, and 10, 31. Now, in the warm-up, we use numbers to represent a certain type of information, dates of non-denominational holidays. In today's activity, we're going to use numbers to represent something that computers use pretty frequently, and that's text messages. Today's going to be a series of challenges, and before each, we as a class will create an encoding system that will allow us to represent that message. And when I say we as a class, I mean you all as a class. I'm facilitating. Okay, our first challenge is to look at the samples, hey, TTYL, and morning. Using only numbers, we want to represent these messages. No letters or characters are allowed, so just numbers or digits. Let's come up with a system that allows us to do this. So at this point in time, if you're simply watching the video, you would want to pause the video and just jot down how you might try to do this. Okay? All right, so what is our system? Now, the system could be very different from one class to the next, depending on what people call out and say. So I'm going to go with something very simple, and I'm just going to say that A is equal to 1, B is equal to 2, and so on, all the way until we get to Z is 26. Okay? So if we just use this system, all right, just let's make it purple. Now I want to use this system to write this message. Oh no. Ooh, I already see a problem. While I can count up and figure out where O and H are, what do I do about the space? Didn't think about the space. So if we're going to fix our system, okay, maybe we have our system is here, and then we have a space is 27. Can we write it now? Can we do this now? Of course we can. So now if I want it now, I had to fix I didn't quite think of everything with the system, or we didn't, I didn't. So we had to add in a space. So now if I want to transmit this, okay, I would need an O, and an O is 15. Then I would need, okay, 15. Then I would need an H, and an H is 8. And let's see here. Oh, and then I need my 27. And then I need my N, which is 14. And then I need my O again, which is 15. Now here's another thing. Ooh, I put spaces in between so we know which numbers are which. Okay? But it's 15, 8, 27, 14, 15. If I squash these together, how would I know the difference between 1 and 5 and 8? How would I know this is 15 and not 58? Something to think about. Okay. Challenge 2. Let's now use our system. Let me go back and get our system. Copy. And I'm going to put our system up here. Ooh. Now I want to use this system to write the message great. Well, I've got a capital G. I can do the R-E-A-T, true? So I can do the lowercase r is 18. The E is 5. The A is 1. And the T, the lowercase t, is 20. I don't know how to do the capital G or the exclamation point. Okay, well, if I did 27, maybe what I could do is say, all right, exclamation point is 28, period, just in case somebody puts one of those in, is 29, maybe comma is 30. Maybe that'll help, right? Let's see here. Let me make this a little bit smaller so we can work with it. Okay, so here's this. But now, you know what I'm going to need? I'm going to need capital A, start with 31. Capital B is going to be 32. And capital Z is going to be 31 plus 20. That should be 56. There we go. So now, if I do this, then I can add in my G. So my G is going to be, my capital G will be 37. And then I've got my exclamation point is going to be 28. Now, the other thing that I could think about doing, if I wanted to run all these together, is I could say everything is 2 digits. So in other words, this could be 0, 1 and 0, 2 and so on. So now 0, 5 and 0, 1, then I can run all of my numbers together and I don't have to worry about anybody getting confused. Everybody's going to know because my protocol is every character is going to require a 2-digit number. Okay, so my protocol, my method of, my system, my method of communicating. Let's try another one. Free at 5, question mark. Well, let's take this and this, copy. Let's go here, pop it in. And then I have, oh, look at that. I forgot a question mark. I got a period, but I didn't do a question mark. All right. Well, I guess, oops, question mark is going to be 57. And then you start saying, ooh, there's going to be a lot of things that I might not be able to write because I don't have an ampersand, a $, a hashtag. I got to give all of those numbers. Got it. Okay. You're getting the idea. There's a lot of characters we have to be able to represent. But first, let's just do free at 5. So free at 5 is going to be 36, and then little r is 18, little e is 5, 5. Now I need a space, which is 27. Then I need little a and little t. And then I need a space. Now I need the number 5. But if I write just a 5, if I write just a 5, that's going to be a problem because I don't know if I mean 5 the digit or 5 the number. And I need a 2-digit number. So let's leave a blank and a blank. And then we know how to do question mark. We got 57. We got to come back in and fill in that question mark. Because up here, I'm going to have to do something like, we could do 0 is 60. 1 is 61. And we go on until we get 9 is 69. Great. Now I've taken care of telling what all of my digits are. So coming back down here, I can put in 5 as being 65. Now I've stayed with my system. My system requires 2 decimal digits, right? Everybody see that? 2 decimal digits. And if I gave you something, you could translate it back and forth based on this system that we have. Okay? But you should notice that even after challenge 3, we got lots and lots and lots of characters that we haven't taken care of. Okay? What about see ya tonight? Well, will we be able to do it? Oh, I think we can. If we take our system, plop it in over here, can we write see ya tonight? 33, and then y is 25, a is 01, space is 27, 2, yes, we know 2, 62, little n, 14, little I, 09, little t is 20, I believe, and little e is 5, and look at this, we actually had the wherewithal to include an exclamation point, so we can do 28. If we didn't have the exclamation point, maybe we'd come in and we could make it 58 or 59 or 70 and go on from there. But see you tonight. This is how we could represent it using just numbers. Now, this is getting kind of ugly, right? Here's the crazy part. All of this has to become binary. So, what we've done is I in this particular video, just invented our own scheme for encoding text with numbers. Given we use text on our phones and computers all the time, we should assume there's a standard encoding for most of the symbols you can type on an American keyboard. Today, we're going to look at ASCII, or the American Standard Code for information interchange. Sorry. You don't have to remember, I'm never going to quiz you on ASCII, what the acronym stands for. You should know that it is a way to map text to numeric values. Now, think about and write down your answer to this question. What is the minimum number of bits each of your systems, or what is the minimum number of bits? How about if we put our system would need per character. How do we know this? Well, we could look at the largest number in our system and convert it to binary. So our largest number was 69, right? And if we take, 69, and we want to convert that into binary, well, got your flippy-do handy? Pause the video and convert 69 into binary. All right, let's do this. If we want to do base 2, we've got to think about, we've got 64 and 128 are powers of 2. So we need 164. The next power down is 32. Don't need that. The next one down is 16. Nope. 8. Nope. 4. Yes, because we have 5 left over. Then we have a 2. So that's a no. And then we have 1. So now we've got 69 in binary. We needed 1, 2, 3, 4, 5, 6, 7. So this required 7 bits. Okay? So that required 7 bits. And again, we converted our largest number in our system into binary. Not really that hard. Now, again, I'm doing all of this in the video. I would want you all to share with the class, and I would ask everybody to pipe up and tell me what the numbers were. Note, there's many possible systems, and there's usually not a right one. So long as everyone agrees, whatever the system is, that system is called a protocol. Okay? Adding more possibilities increases the risks of having too many characters to represent and not enough bits to do it. This is a practical example of the overflow and rounding issues from the previous lesson. We get so many different characters. Remember, we're just looking at the American keyboard. There's lots of different alphabets out there. And those people, those nationalities, they want to see typed, printed text in their character set. So we need a lot more characters. First, you do not need to memorize this table. This is the ASCII table. Just understand that it exists and the underlying principles, that it maps characters to values. So null is 0, okay? And notice, we have all of these things. Some of these things, that's a bell, an NQ, a NAC. These are some things you don't really have to worry about. It's things that the computer does. But an exclamation point is the number 21. Double quotes is 22. Hashtag is 23. $ is 24. Plus is 28, or sorry, 2B, and so on. By the way, these numbers are in hexadecimal, meaning base 16. 0 through F is base 16. We haven't talked too much about that, but suffice it to say it's there. We come all the way down here, and this is our complete table. Now, what is the same? Think about what's the same. Well, we used numbers. We used numbers to represent letters. What's different? This one is in base 16. We just used base 10 or decimal. We also didn't use all of these things up here, which include some special characters that are used by the computer. What's interesting or surprising about the ASCII system? It's pretty complete. They've taken care of punctuation and letters, both capital and lowercase. A lot of stuff. But you also realize that the ASCII table is not complete. Notice 77 to 86. We now actually use something called Unicode, which adds more bits because it also takes care of all of those other alphabets that aren't taken care of here in the American standard. The U.S. was one of the leaders in computing technology, and as problems arose, we solved them for ourselves first. But then as computing became more and more global, we became more and more of a global society, we had to come up with a way that the U.S. could talk to Japan, could talk to Russia, could talk to everybody, and they could talk back to us. We needed to be able to convert back and forth with everybody's characters. Now, let's look at our vocabularies. Abstraction. It's a simplified representation of something more complex. Abstractions allow you to hide details to help you manage complexity, focus on relevant concepts, and reason about problems at a higher level. Okay? When you drive a car, there are abstractions. You have a steering wheel. You turn to the left, you turn to the right. You don't have to know that the steering wheel is connected to the gear shaft. It's connected to all these other things that go to the tires, that then turn the tires left and right, that make the car turn left and right. There are levels of abstraction. You only need to know what to do with the steering wheel. Abstraction, a simplified representation. ASCII, American Standard Code for Information Interchange, the universally recognized raw text format that any computer can understand. And yes, there's a couple of typos there. Protocol, a set of rules governing the exchange or transmission of data between devices. Our system was our protocol. It was the rules we set up in order to exchange information. Okay, take a moment and write down your answers in your notebook to the following prompts. What problem were we trying to solve today? And what details from the last few lessons were hidden or were out of focus as we solved our problem? Pause the video and write this down in your notebook. Okay, what problem were we trying to solve today? Well, we were trying to solve text messages. We needed to come up with a way to map text to just numbers. We needed text characters, punctuation, and we even needed the digit characters. Now, what details from the last few lessons were hidden or out of focus? We were using base 10. We talked about letting things be 1, 2, 3, 4 instead of binary. This made it much easier, but it hid how many bits would be required to represent all the characters. At the very end, we had to take our largest decimal value, convert it to binary to determine the number of bits. Additionally, those bits, well, those just represent electrical impulses. So there was a lot of abstraction today. Computer science deals with multi-layered systems, so we need to create easier ways for humans to keep things straight in our heads. This is abstraction. We don't want to remember all the details. We find a simpler way of representing something complex, so we can temporarily ignore that underlying complexity. An example, computers can represent text. We don't need to know how it does it, just that it can. Under the hood, each character is really just a number, which itself is a binary number, which comes down to being just a bunch of electrical impulses in a wire. We do not need to think about this all of the time. If we have to map things, we could just say that A is 65 and sweat the details only when necessary. That is how we send and represent text.